Thank you, John. Yeah, it's a real pleasure to be here. Thank you very much for the invitation. Indeed, I have known John since 1991, I believe. I don't think we went to sea together. John went on many, many more cruises than I did. I only went on a couple of big cruises in the 90s. But it's a tremendous experience and a privilege to go to sea, do important research, and John has a lifetime of that. So, just want to sort of pay my respects to you, John. But thank you as well for giving me an interesting topic. I think I can cover this to an extent, but I said earlier to John that I don't think anybody can be an expert in all of this. It's almost too big a topic. So I had the sort of good fortune of being able to work around climate modelling, so the ocean primarily, but other aspects of that as well. I will try to answer the question. I'll probably be a bit ambiguous and to some extent sort of conditional on answering it. I might sort of say at the end, in a nutshell, what I think. First of all, I'm going to kind of set the scene a bit. I'll tell you a little bit about where some of this kind of modelling comes from, the basic sort of ideas around that, a little bit of myself as we go along in terms of how I came across some of this information or even met some of the people, or in some cases did a little bit of the work, and then I'm going to step into a little stepwise how you make a model in 6 not very simple steps. I'll talk about what then happens next, what you see as a consequence of making one, what we do about that. There's a lot more work after you've made the model before you kind of can make sense of what the model can do. I'll reflect on how bad they are, as well as potentially how good they are. And then I'll take a little glimpse into the very near future of modelling, which is accompanied by the near future of climate change as well, of course. So there's a whole purpose to this. Right, so you see in the background there, I've sort of faded out an image that will come back a bit later as an animation. So you can be sort of waiting for that to come back. But what you see is the global ocean and a kind of very elaborate pattern of ocean currents, which are indicated by the whiter shading, basically. So it's a complicated world, and that's what we're kind of up against. This is one of the finest simulations in the world, but I'll come to that quite soon. So I know this is a busy slide. Some of my slides will seem a bit busy. Partly the point is to sort of emphasize the detail that we need. I wanted to sort of start then with this early days reflection, and it's not that long ago actually, but it was kind of the dawn of my career. So I did my degree in meteorology actually at the University of Reading because I wanted to be a weather forecaster, and I never turned out quite that way. So I learned by year 3 of my meteorology degree that the ocean was an important player as well. So then I went to Bangor in North Wales and did a 1-year master's degree in physical oceanography. That's a lovely place to spend a year. But I was determined to get to the US because I was young and impressionable, and I thought that the only place to really kind of prove yourself would be a much bigger, brasher country. So being young and impressionable and fortunate as well, I managed to get a job for just 1 year at a place called Oregon State University, which is quite an important centre of oceanographic science in the US. So that's in the northwest corner, north of California, and I spent a good year there. The remarkable thing about that year was that I arrived in September. I enjoyed a lovely kind of experience of what they call the fall, quite a mild winter. Spring came really early, as it does in that part of the world, much earlier than it seems here. And then it started to get warm, and it got warmer and hotter and dry. It didn't rain for months on end. And that was the summer of 1988. And that summer was quite an epic experience for the United States because of tremendous drought and heat waves. I think in the modern context, they were probably not so severe, but at the time, it was very dramatic weather. It caused a lot of trouble for agriculture. and I experienced 100 Fahrenheit for the first time and things like that. So coincidental with that, this very important scientist called James Hansen testified to the US Congress. It was a coincidence. I think this had been building up for a few years. So during the 1980s, climate science what was probably led from the United States to a large extent, and there was a strong body of opinion that carbon dioxide was consequential for Earth's climate. So Hansen was one of the real pioneers of this story, and his testifying to Congress here on the 12th of June 1988 was regarded by many in the climate community as one of the sort of real early turning points in governments taking climate change seriously. So Mrs. Thatcher actually also began to take climate change seriously, and around the same time effort went into developing a sort of international cooperation to really work hard on this emerging problem, which at that time didn't seem so bad because temperatures had not yet risen very much. But just to sort of give you a flavour of what I'll be saying and talking about, and I want to emphasise that climate modelling is essentially a story of remarkable people. So not just James Hansen, but many others in the early days of the 70s and the 80s did the sort of pioneering work, which I'll probably refer back to a bit. And in the 1970s and really moving into the 1980s, Hansen and colleagues pioneered this research on what was then, and still is probably best understood as the enhanced greenhouse effect due to rising CO2. So Earth has a greenhouse effect due to primarily water vapour in our atmosphere, which prevents us from being too kind of extreme in our climate, basically moderates our climate. Helps to trap some heat usefully, but carbon dioxide has enhanced that natural greenhouse effect. And during those early days when computers were smaller, which is a theme that I'll come back to, Hansen and colleagues used what we call 1D computer models. So 1D means one-dimensional. So instead of latitude, longitude, altitude, depth, it was just altitude, but really depth, because the ocean was already believed to be most important for slowing down the rate of global warming. I am not going to try to explain this diagram, but that's just a iconic diagram which primarily emphasizes this thing called unrealized warming. And what that really amounts to is the slowing down of climate change or warming by the oceans, which have an enormous appetite for extra heat. So they kind of draw down heat which would otherwise stay in the atmosphere, if you like, and that helps in these very early, quite accurate predictions of climate change. So even at a time when we had limited computational resource, it was possible with limited computational resource to make these quite accurate calculations of how much we expect warming associated with the amount of carbon dioxide that was building up in the atmosphere. So way back in the late 1980s, under the presidency of Ronald Reagan, soon to be the first George Bush, Congress was willing to hear from Hansen, and that was a really important moment for me as well, because I realised this was going on. I was only 23 years old, but I had a sort of inkling that this was something important. I say fast forward to now and show a busy diagram, because what happened next was that everybody got a lot more interested in climate and climate change. So Hansen and his colleagues pioneered the way for, quite soon afterwards, an international coordination. And many of you will have probably heard of the IPCC, which I think is an acronym shared by a police complaints authority. But the IPCC, as I discuss it here, is the Intergovernmental Panel on Climate Change. And the first one was in 1990, and actually I just started working at a place called the Climatic Research Unit at the University of East Anglia when I came back from my travels, and started working on the aftermath of the so-called AR1, the first assessment report. That's a FAR, actually, the FAR. So this first assessment report was quite small in sort of length, and probably was still a remarkable document at the time, if you take a view of it in the context of 1990, because it did highlight most of what we now have confirmed and what we still care about in terms of how Earth's climate is changing. And on we've gone since then, and every approximately 6 years, the IPCC essentially updates its report, in various components, and we're presently just gone past the 6th kind of cycle, so we're into the 7th. And the latest one was published around 2021. They come out in a staggered way. There's usually 3 parts to that. There's the scientific assessment is the one which I'm most familiar with, but there's also a couple of others about adapting to climate change and mitigating climate change. Anyhow, we have this sort of headline summary for policymakers, and one of the headline figures of the headline summary is something like that. Now, I've only put it there because it's trying to reduce what we most recently know about present and future climate change to a relatively sort of simplified set of information, but I still think it's quite hard to look at that and figure out what's going on. It's essentially a range of scenarios based around various amounts of global average temperature rise, and the temperature rise of 1.5 centigrade has been politically raised up as a sort of a target after a meeting in Paris not very long ago. This now seems probably already we've reached there. We're probably heading for 2 and maybe a little bit more, maybe 3 sometime during the 21st century. So I think the point I make at the bottom there is that peering into the future across this very wide range of decisions that we might make around technology and lifestyle, kind of collectively, individually, globally, that kind of peering forwards is entirely dependent on our ability to model the climate. We can't just kind of make this stuff up. It has to be based on some really quite delicate calculations, and whether you're interested in the heat at the bottom of the atmosphere or the amount of soil moisture that may or may not be there in the future, or how wet it's going to get. These are the things that kind of government and public want to know about, but to get there we need to do some basic thinking. So I'll just take you through a few backgrounds, principles, I suppose. I don't really want to dwell too long on things like this slide and the details therein, but these are the iconic figures or images that we often use to summarize where we are in the sort of first principles of understanding our climate. So what you see here is lots of arrows pointing downwards and upwards with numbers associated. Those are amounts of energy per time per square meter, basically. So that's kind of the essence of our climate, is how much heat is coming and going from beyond our atmosphere, within our atmosphere, interacting with the surface, be that land or ocean. And although it looks busy, this is highly simplified. This is a sort of state of our knowledge of those numbers in 1996. So this is the second assessment report of the IPCC, the SAR. And at that time, there was a reasonable amount of confidence in these numbers, plus or minus 1 or 2. So these are kind of important numbers because it's the slight perturbation of the outgoing long-wave radiation, which is at the core of understanding climate change, because that's the bit which is affected by carbon dioxide. Anyway, if you're going to build a climate model, you've first of all got to kind of know this kind of thing. Then I'll say a few words about what we're really kind of up against here, which is what we generally call dynamics. So in physics, the word dynamics, it alludes to things moving around, and fluid dynamics suggests that we're looking at fluids moving around. Now, fluids are the obvious thing, water, which is found obviously in the great oceans, but air is also, in some sense, a fluid. The way that we understand its kind of mobility and the way it kind of carries heat and moisture around, actually. So the picture there is just kind of a starting point for how climate works. You often want to start somewhere. It's quite difficult because the whole thing is circular, but we can start perhaps at the equator with the overhead sun shining down as if on this nice glitter ball up here, right on the sort of axis of the Earth, kind of where it's rotating at the equator there. Now, a lot happens down on the equator, which has consequences for everywhere else. We often start there because the heating of the lower atmosphere makes the air buoyant, so it rises. All the water vapor that comes upwards in gas form is condensing out into clouds. That releases lots of latent heat energy, which powers the atmosphere, makes it move even more. So what's going on here is that we have this kind of combination of air moving upwards but also sideways, and collectively we have these great cells of air moving sort of towards the equator near the surface, rising up, forming clouds, and then heading off north and south at high altitude, maybe about 15, 20 kilometers high. This makes kind of a circular kind of cell, which was first understood way back in sort of Georgian times. So George Hadley sort of first discussed this, and I think later on in his honour, these motions were named the Hadley cells, and they're really central to Earth's climate system. Much more beyond that goes on. I mean, this explains to some extent the existence of great rainforests where you have ample rainfall as a consequence of all this ascent of air. That air has to go down somewhere else. It sort of dries out as it goes back down towards the Earth's surface, and consequently the very dry conditions are established for the major deserts of, say, the Sahara. So this is all very important because it implicitly involves moisture, which is one of the keys to understanding climate as well, by the way. Heat and moisture, that's really what it's all about. Now I've introduced so I wrote a book during lockdown, partly during lockdown, and as we all had lots of time on our hands, and I was already writing it, but it took on a bit more of a central kind of part in my kind of daily life. And so the book was about the oceans, written for my students, primarily all students that are studying oceanography, and it was about ocean currents. And so I spent a lot of time thinking about how the ocean moves around, which of course I already know about, but I thought about how to sort of show that off a bit. And often what we do in science is we try and simplify things into these kind of cartoons or schematic pictures, and this is one of my more difficult endeavours. This took kind of one Saturday morning, rather agonisingly, trying to get various things looking about right. I don't want to kind of sing my praises necessarily, but just to sort of explain to you that this is my best way of showing you that the ocean also moves around like the atmosphere does, which otherwise we know as the winds. The ocean is busy moving around via these currents, and so various things that I don't want to go into detail here, but the fact is that the consequence of the sun, which is the big yellow blob in the middle there, heating the equator, as I just showed you on the previous slide, from the atmospheric perspective, and lots of other squiggly arrows communicating between ocean and atmosphere. Also the winds, which I don't show here, but the winds are very implicit in moving these big horizontal kind of what we call gyres. And then below we have tremendous movement of various waters, north and south. This is an idea of looking from the north down to the bottom right to the south, over in the sort of top left. So this is kind of Arctic to Antarctic perspective, and this is a kind of a view of the Atlantic to some extent. Now, these ocean flows are as important as the atmospheric winds, and if we take one just regional perspective on this, this is another figure that we prepared for our book, just to demonstrate how important the oceans are for local climate or regional climate. So the colour you see here is a temperature between -20 and +20, and it's the local departure from the average for that latitude. So here we are in Romsey, which is approximately 51 north, I think. So if you look sort of sideways, east and west, you can go to, you know, central, I guess, Russia, onto Siberia, or over to the interior of Canada, approximately the same latitude, and you find a very different colour. So our colour is about 10, so 10 degrees warmer than the average for 51 north. But if you go over to sort of Hudson Bay or over to the far east of Siberia, you know, Vladivostok or somewhere like that, you find colours that correspond to -10 or -20. Now, that is all because of, in January, which is the particular time of year when this is most extreme, the enormous amount of warmth conveyed northward by those very currents I just spoke about. So the big arrow just shows you that that's going on. This is something we need to think about when we model the climate. We need to get the ocean right. And why that matters is that it doesn't happen in a nice, very sort of regular, constant way, but it wobbles around this kind of movement of heat. And so actually I'd ask you to start looking at the bottom right picture, which shows a kind of pattern of red, blue, red. And that's without any kind of indication of how much that is in temperature. It's plus or minus 2, basically, centigrade. And this corresponds to a pattern of temperature warmer or colder than average in a particular March of a particular year, so March of 2010. I think we're all old enough to remember, if we can cast our minds back nearly 13 years, that this was a very unusual, dry, cold, snowy winter. So although it was dry, it did snow, and the snow hung around. So seen from space, the Britain looked like that. It was a very white island for a short time. And that's associated with a pattern of change in the Atlantic, associated to an extent with the currents, which set up this unusual pattern of temperature in 2009-10. If we go forwards a few years, a very different picture emerges. This is actually the mirror image of sort of. So we now have a cold, warm, cold. Previously had warm, cold, warm. So this is kind of the opposite of that pattern, and it's kind of the opposite of that weather type. So instead of having a cold, dry, snowy winter, in the winter of 2013-14, which again we might be able to remember, it rained a lot, and it rained a lot in the south, in fact, and that's the Met Office data for January 2014. So the ocean contributed to this, and we have very variable winters in the UK because we're very exposed to the North Atlantic, and the North Atlantic is a very variable ocean. I'm just moving around latitudes, so I just want to mention, apart from mid-latitudes, which is, so I started off at the equator, I've mentioned there our latitudes, what we call the mid-latitudes. If we go to the poles, this is a bit of a challenge for all kinds of reasons. So for a start, it's not just atmosphere and ocean, but there's also ice. And ice is kind of a bit of a joker in the pack somehow. It really causes a lot more trickiness when it comes to modelling. And there's a big contrast between the north and the south. Of course, the Arctic Ocean, although it is generally covered with sea ice to an extent, although that's declining, is an ocean. It's quite deep in the centre. It's got some very shallow flanks. So these are called the shell seas of the Arctic. It's only about 50 to 100 metres deep. The centre is much deeper. It's proper ocean. So that would be like 3 or 4 kilometres deep. Utterly different if we go and look at the southern hemisphere from below. We see that Antarctica is, of course, sort of slap bang in the middle, and that's all land, covered by an ice sheet for many millions of years now, but surrounded by ocean. So that's called the Southern Ocean, and the Arctic Ocean is surrounded in turn by North America and Eurasia, as well with an ice sheet, by the way, which we care a lot about. Greenland sits there as a kind of relic of past glacial times. It's almost like a hangover from the last ice age. And Antarctica is more permanent. So this is tricky because it adds difficulty to what's going on. And one of my current research projects called Arctic Connect, it's about 2/3 the way through now. It's a 4-year project. And in Arctic Connect, this is our sort of logo, scaled up or blown up. We're concerned about how the Arctic, as it changes, which in fact we know very much is going on, is impacting on middle latitudes in particular. So how it connects to lower latitudes. And all these little details in here are indicative of how the ocean might be changing, how the atmosphere might be changing as a consequence of what is going on up north. And there's a lot of decline in Arctic sea ice, and it's getting warmer. So that's something which I'll mention in passing, and that involves modelling too. I think my final slide in sort of setting the scene is so far I've talked about what is generally physics. So that's kind of what happens to air and water, heat, dynamics, and putting all that together in itself is a challenge. But things are complicated in the climate sort of picture by complicating chemistry. So first of all, we need to care about what's happening to various gases in the atmosphere. Obviously, carbon dioxide is important. It's quite inert, by the way, but there are other more reactive gases. But carbon in itself is, of course, a building block of life, along with various important nutrients. So it turns out that physical climate is intimately linked to carbon cycling, which is the movement of carbon and carbon dioxide through the atmosphere and the ocean. And that picture there actually is kind of one of my sort of favourite achievements, or not mine, but I mean one of the favourite achievements I recognise of my colleagues, to piece together all the different information collected on research cruises to establish where carbon dioxide has got to so far in the ocean. So it's coming from the atmosphere and going down. And if you look at the vertical scale, it goes down to 500 and then accelerates kind of beyond there down to 4,500 meters. So most of the carbon dioxide that has got into the ocean, which it does by dissolution, has so far penetrated over the last 150 years of industrialization to a depth of maybe 500 meters. So it's clearly taking away quite a lot of the carbon dioxide that would otherwise stay in the atmosphere. So this is an important big detail in climate modelling, which we need to get right. And further, carbon is linked to nutrient cycling and life. So all of these things together, we collectively call the Earth system. So that's the physical and the kind of geochemical world we live on. So the chemistry of what's going on in the atmosphere and the ocean, and the way that determines life cycles and how much carbon is fixed, how that ultimately affects the surface of the planet on the land, but also in the ocean, how much life is being kind of disrupted by some of these ongoing changes. To check the time, I realise I might go, hopefully not too long. So it's now coming up to 8 o'clock. How long should I talk for? I will try. I'll try and sort of go a bit faster. I've kind of set the scene. I don't need to talk quite so lengthily. I wanted to just go through these 6 steps of building and running a climate model. So I'm going to go through them. There's some summary pictures of what I'll show you. We need to establish rules of the game. We need to chop up space. We need to choose some geography. Then we need to code, which is a computational activity. We need to couple things, which I'll explain, and then we need to number crunch. And in brackets, we need to tackle the data deluge, which is kind of a big sort of part of the problem. So look, this is just the really nitty-gritty of what we are working with. So it turns out for the ocean and also the atmosphere, you can get away, or you only need 7 equations to really calculate everything you need to know about that system and what's going to happen to it next. So very simply, I hope, don't look at the equations, but just look at what I've written down on the right-hand side. What we care about to calculate currents and keep track of seawater, basically, is to know how much things move east to west, how things move north to south, how things move up and down. Those are the equations that relate to those statements. We need to account. So we're kind of like accountants at the end of the day. We're just kind of spreadsheeting things in a grand fashion. We need to keep a tab on volume. That's how much water's coming in and going out of a given space. We need to account for heat. We need to budget for it effectively. And we need to do the same for salt. The ocean's a salty place. And finally, we need to track what we call the density of seawater. So that's just how many kilograms we get for every meters cubed. And that depends intimately on the temperature and the salinity, which is basically the heat and the salt. Okay, so the second thing we need to do is apply these equations everywhere on the whole Earth, if indeed we're concerned with global scales. So I've just shown you 5 examples of how very smart people have chopped up the surface of the Earth, primarily with a view to ocean modelling, although it goes over the land in some cases. There's some really quite bizarre thoughts go into this, but it's necessarily so because the Earth is inconveniently spherical. And that means that when you chop it up into latitudes and longitudes, things vanish to the North Pole, which you see in the, I'll use my pointer for the first time, this is the great problem of latitude, longitude chopping up, which is why, in a bizarre way, which I can't begin to explain, people have thought of making a third pole. One's on the land of Antarctica, and the other two are placed on the land masses of Eurasia and North America. And this gets away from the problem, because we don't care about the land if we're oceanographers. We only care about that bit which is currently ocean. Anyway, let's not get too far down the rabbit hole. There are some really smart, interesting ways of alternatively thinking about chopping things up. But what we're really doing here is we're working to continuously update our currents, temperatures, salinities on what we call this grid of points. So we're splitting the world into small elements or grid cells. This is the language of modelling. And we're defining, therefore, these grids or meshes, some of which I obviously have impressed on you are innovative for some clever thinking. And we have to do the same vertically. So what these pictures are showing is some background colouring, which is temperatures going from high to low maybe. Or this is probably actually density. But anyway, what we need to do is somehow cut through this, chop it up so that we capture that vertical gradient or variation of temperature from warm to cold. And we can do that in different ways. And I'm not going to go into the details. But depending how we do this, and there are three choices here, there are consequences for how we capture the complexity of the world ocean bathymetry, which looks a bit like this. Now, this is a very high resolution, a wonderful product produced by people who spend their entire career. This is stop being a pointer, but never mind. So where you see places of kind of extreme change in colour, you have dramatic sort of sheer drops in the deep ocean. You see some of those well-known geological features like spreading ridges and abyssal plateau, very narrow gaps, which are really consequential for how water moves around the world's oceans. So this is at a high sort of spatial scale, fine spatial scale. And the same applies to capturing the orography, or the sort of the mountains and valleys of the land, because the atmosphere also cares about that. So if you have a big mountain range, it's going to be wet on the side from which the winds are blowing, and it's going to be dry on the other side. So you have a windward and a leeward effect on the rainfall, and that can be sort of at large scale understood as consequential for climate itself. So yeah, we need to basically choose our geography very carefully, knowing what we can do with our coordinate system. And then when we've done what we need to do to choose our equations, to chop things up and to choose our geography, then we need to start the work, the real work, which is to write the code, which is the model essentially. And I'm going to tell you very briefly about the language that we still use, which I think is really a remarkable story, is Fortran. So I don't know, hand up if you write Fortran code. That's great to see. So you have to be a certain age and vintage to write Fortran. My young colleagues don't know what they missed out on, I don't think. So I don't know whether you know, but it's argued about whether it stands for Formula Translating System or Formula Translator or Formula Translation, but it was developed as long ago as the very dawn of computers, really, in 1954. So I think it's great that software and hardware obviously kind of were sort of running in parallel at that time. And this kind of hero, I guess, of the early days, John Backus, was the person who led the team that developed the early semblance of Fortran to program the IBM 704 computer, of which I have only a picture. I know nothing about these early days. So Fortran, in those kind of points on the side, developed hand in hand with the computers themselves. The computers are, the centerpiece here, of course, because following the Second World War, Bletchley Park and some innovations in places like Manchester, a couple of other places, computers evolved from those very early stages of, transistors through to later on silicon in the 1960s, I think. So I'm not very good at the sort of technical hardware, but I can tell you that this is the most important stage in sort of the dawn of computing. It thus became the most efficient way to program computers for big tasks, because Fortran developed with the computers. It just kept up with them. Computers kept up with Fortran, and Fortran kept up with the computers. And climate modeling is one of the biggest tasks around. And by the way, on the sort of journey to the modern day, Fortran played a leading role in NASA's Apollo missions, and it definitely helped Apollo 11 to land on the moon in July '69. We know that Neil Armstrong took over for the last few seconds, but he was helped most of the way down by Fortran, I think. I just thought I'd show you, that's what it looks like. We call it main because it's the main part of the program, which comprises many of the bits and pieces. So we build a kind of structured framework of computer programs, one of which controls all the others. And so this comes from a project I was involved with around 2000. For the following sort of 6 or 7 years, we built an Earth system model called Genie. And this was a real interesting period of my career when I learned how to couple models together and do things very effectively with computational code. That has really kind of more of a kind of small-scale activity compared to the great communities that have evolved over the last 30 or 40 years. So the big climate models we have comprise components for, say, the ocean or the atmosphere. I know most about the ocean, and there are probably 3 or maybe 1 or 2 other primary singular sort of clusters of code that are literally communities of people that write the code, and has quite a long sort of history usually, and it's now very established. So in the case of the first one up there, GFDL stands for the Geophysical Fluid Dynamics Laboratory at Princeton, New Jersey, US. A related code which kind of offshoots from that comes from Los Alamos. It's interesting that a lot of these technological things, and I'll mention another one later, have their roots back in the Manhattan Project, I think, of the Second World War. In fact, the legacy of those of that project was to leave great centres of computational innovation. Anyway, so the MOM codes come from GFDL in the US, and the US tends to use those in their climate models. In Europe, there was a revolution around the 90s into the 2000s when this thing called NEMO, the Nucleus for European Modelling of the Ocean, there's a French version of that which I won't attempt, which has taken over our climate modelling here in Europe and actually across much of the world. They build engines for the ocean, blue, white, green oceans, which is kind of the water, the ice, the life. And it's used in many climate models, as I say. The last one, I was involved in this, the predecessor of this, MICOM, in the 90s. That's how I got involved in ocean modelling, but it's sort of hybridized into something called HICOM. I don't want to say any more about it, except that it doesn't seem to have gone as far. So it's really the sort of GFDL and the NEMO worlds which we live in. The fifth thing I want to mention is that we need to then take our ocean model, which might be this thing on the right-hand side, and we have to couple it with using all that fancy exchanging of energy and water with an atmospheric model here on the left-hand side. So what I'm showing you actually is the surface wind around the Southern Ocean. Interesting thing. The reason I'd made that picture was because on the 13th of January 1993, for which that picture was kind of extracted very retrospectively, I was in that little purple dot that you can just about see in the South Atlantic. And the reason I'm excited about this is because that was one of the biggest storms that I've ever experienced. We had to suspend operations for 3 days and bobbed around like a cork in the research ship Discovery for a while, doing absolutely nothing, waiting to be spared, basically, because that was a tremendous experience of the power of nature. Now I could go back sort of 30 years later and extract this retrospective, what we call a hindcast or reanalysis of the atmosphere at that time, which has come from an atmospheric model itself. On the right is the much more elaborate system of currents around the Antarctica, and there's a big contrast actually between the scales on which the atmosphere and the ocean go about their business, and that's one of the great challenges that ocean modelers have compared to atmospheric modelers who have it way easier than we do. So yeah, this is the Genie system model. I just want to show you this because it shows in a very kind of simple but maybe elaborate way as well how the model exchanges heat, for example. We could do the same for fresh water. So on the left is the heat flux into the ocean, and on the right is the heat flux into the atmosphere. And they kind of match each other, but not entirely for good reason. So I just wanted to show you that we can do this in a very exact way, in a very simplified setting, so much chunkier outlines of the continents here, because the reason for doing this work was to make a very, very crude but very fast, computationally fast model to simulate hundreds of thousands of years of Earth history. So I'll just mention in passing that coupling matters, whether you're coupling in a sort of simplified system or a much more elaborate system. But ultimately, coupling is vital. This is way too busy, but I just want to sort of emphasize, in order to progress from coding up and the coupling to actually executing the job and number crunching, we need high performance computing now. Which is another way of saying that we need as much as we can get our hands on. I'll come back to this later on. In the UK, the Met Office for the weather forecast and the climate modelling uses a machine. These are big, elaborate, expensive, energy-hungry machines that do unbelievable amounts of calculation in short time. So Monsoon belongs to the Met Office. They have a separate building for it. That's how big and sort of heavy duty this activity is. And the UK otherwise offers its research scientists, who maybe are astrophysicists or molecular biologists if they need to use supercomputing, or climate scientists, something called Archer 2, which has its symbol at the bottom there. So that's currently the latest version of it as of operational since November 2021. Lots of detail, I don't want you to worry about that. I just want to say that this is a figure from a paper which has on the x-axis 2006 to 2023, which is now. And on the y-axis is what we call a non-linear scale, showing just how fast the computer is in a unit I'll come back to. And there was a kind of progress going on up until the mid-2010s, but I think things have stalled a bit. So the brackets "we're behind schedule" refers to the fact that we might not be making quite the progress we would like with computational technology. However, there is a kind of a good side to that, which is, now the reason for doing this is the bigger the model and the faster you can run it, the more data it creates. And data is kind of a modern curse in some respects, because I just showed you a very limited, tiny sample of the kind of mesmerizing number of, these are files. Each one of those corresponds to a month of a variable on a small piece of the Earth. I mean, I just kind of cut this out to do some analysis. But anyway, we get millions, possibly billions of files. Each one of those is huge and needs to be carefully interrogated. So this is just a sample of some data. I don't want you to sort of think that I'm this boring, but this is kind of the world we live in. If we want to do, if we want to use a climate model, we have to confront the data that comes out of it, which is terrifying and not much fun sometimes, but can be done with good technology. So now I'm just going to go backwards slightly, back to the dawn of computing. Why am I doing this? I want to take you quickly on a journey to where we are, using those 6 steps that I've emphasized. So modeling the oceans, so that's what we do. That's what I do. Things were going on quite well in the late 1940s and the early 1950s. Our predecessors, you know, John would have met some of these guys. I think you, Sverdrup and Stommel. Yeah. So they are the real pioneers of understanding how the oceans moved. And Stommel was a brilliant man. Worked at Woods Hole in Massachusetts, I think, most of his career. And it's only once we got our hands on some computers that we could go beyond their original genius, which was to more fully explain how the oceans work. And this very crude set of 4 diagrams here shows the first tentative steps into computer modeling of the ocean, which is fundamental to building a climate model. And that was published in 1963 by Kirk Bryan. I think it's Kirk Bryan. So one of the pioneers as well of getting hold of a computer when those were very novel, and making the model try and do something a bit more elaborate each time. So what I'm trying to show you here is these are the sort of very early steps towards model realism that we see. I'll come back to that in a second. So in the North Atlantic, we have a strong flow on the far west side and a much weaker flow on the east side, and that's called the Gulf Stream. And in order to model the Gulf Stream, you have to get some physical things and dynamical things right. And that was the very early steps towards that. I want to also emphasize then this idea of resolution, which is just how big the sort of chopped up bits are, or how blocky the outline is. So this is supposed to be Europe in the first assessment report of the IPCC in 1990. The second assessment report is 96. TAR is the third assessment report in 2001. And the AR4 is the fourth assessment report. They couldn't call it FAR because they already had a FAR, so they called it AR4. And that was in 2007. And what you can see is kind of the emergence of the Alps, if you look very carefully at the progression there. So orographically, the landscape of the Earth began to emerge realistically because we were able to afford to chop up into smaller pieces because computers were getting faster and faster. But other things were going on too. So I've got the same pictures there and just recorded those four assessment reports. And by the way, it carried on. So AR5 2014, AR6 2021, I mentioned already. We're in the AR7 cycle, not much said about it yet. I guess that the next report will be due 2028, but there's a lot of debate about this process and whether we should really be just churning out a report every 6 years, which is only slightly different than the last one, to be honest. That's just a personal view, but the other thing that's been going on is that in climate modelling from the mid-70s to AR4 in the sort of mid-2000s, we've moved through complexity. So the complexity is to add things. So clouds got better by the mid-1980s. An ocean... No, sorry, I'm going the wrong way here. No, I'm not. So the first assessment report, the important thing was that the ocean appeared, but as a swamp, which meant that it didn't move. By the second assessment report in 96, the ocean did move. And by the third assessment report, there was more going on in the sort of atmospheric chemistry. By the way, they had volcanoes, the carbon cycle started to appear, chemistry got more elaborate still, and vegetation appeared. So climate modelling has involved adding more and more detail to how we know the planet works. We need to care about what kind of vegetation grows, how it responds to the climate system. We need to do the same in the ocean, actually, to get the plankton right. So increasing resolution in the ocean here is shown by going to much higher resolution than they do in the atmosphere necessarily. So from 1 degree to a quarter to a 12th. And that corresponds to 100, 25 and 9 kilometre scale grid cells. And by the time you get to 9, you can't see the grid cells anymore. You can't really see them very well in the quarter. This is called Orca 12. I'll refer back to it. So this is the Gulf Stream. As it moves up the eastern seaboard of the US, it becomes unstable and forms these meanders, which are really important for lots of reasons I won't go into. You can see that the 1 degree model is impoverished by comparison. So it looks pretty good at a quarter, but we know that the 12th is way better. It's really expensive to run a 12th. A quarter is about as high as it goes in a climate model, but we use a 12th sometimes, which I'll come back to. And there's a couple of extra things I thought I'd mention, or one extra thing that I'm sort of personally close to. So about 12 years ago, I had a grant funded to introduce icebergs into ocean models, which was done by some extra computational work and a few years of effort to get to this point where you see these two diagrams showing the amount of iceberg presence in the north and the south. There's a lot more icebergs around Antarctica than there are around the Arctic. Icebergs are important because they take the ice away from the ice sheet and they kind of gradually melt somewhere else. So instead of just sort of putting ice straight in as water, you accurately model the movement of ice away from its origin, and where it melts is somewhere else. And so finally we get to kind of a star of the show kind of thing, which is a climate model showing here approximately, well, it's going to work through several months of a year and then repeat, I think. And what you can see is a lot of activity going on top of an ocean. The ocean is moving very slowly in the background because the ocean moves a lot slower than the atmosphere. The atmosphere is kind of pretty busy by comparison. And what's shown is the amount of moisture which is associated with storms. In fact, if you look closely, you'll see Amazonia flashes on and off daily, because at the end of each day there's rain. I don't know whether anyone's been to the tropics. It tends to rain in the late afternoon. And this is a model, and this is a remarkable achievement by the Met Office and the National Oceanography Centre, who respectively brought together the highest possible resolution atmosphere called N512, which can resolve the weather, which is normally absent from these kinds of climate models, and Orca 12, which is resolving the ocean as best we can. And they're communicating with each other, and they're demonstrating some really fabulous, realistic behaviour. There's a lot more to say about it than I have time to dwell on. If we take the ocean speed, just take the atmosphere away and speed up the whole movie, now you can see that the ocean is moving and it is doing things a bit more like the atmosphere on the previous slide. One interesting thing, you see there's kind of a flickering, almost a ghostly flickering of the ocean, and that's a response of the ocean currents to the passage of atmospheric weather, basically. So as a storm goes quickly past, it sort of excites the ocean briefly. What you also see are this kind of meandering and breaking away of like loops and what we call eddies all over the place where we have a strong current. There's quite a lot going on around the equator, which is quite an important place for climate. Currently, the El Nino is developing in the Pacific. But I must move on. So how bad are they? I don't have much to say about this because it would take too long. This is just an example of how varied the results are. So if I hit my button again, we get models disagree from observations, which we kind of regard as truth. They differ from observations, but they disagree also with each other. This summarises just how awfully warm the Southern Ocean is in the very best climate models of the UK. Those temperature anomalies are way too large, like 4 centigrade. The problem is that the ocean's a busy place. I am going to finish quite quickly if you don't mind. So what we're showing here is all the different things that go on inside the ocean that are so difficult to understand. We can't even measure much of this stuff, but they control global currents and climate. They're hard to model. The atmosphere is just as bad because clouds are one of the great problems of atmospheric science and modelling. There's a lot of microscopic processes with global consequences. This is all hard to model too. The future, just a few more slides to kind of make us feel better. There are prospects to do something remarkable with the more amazing computing power that lies beyond, and we might need some machine learning and artificial intelligence to help us get there. But what you see on the left and the right are the kind of very detailed simulations of sort of idealized flows in the ocean, clever ways of capturing detail with an adaptive grid, it's called. We're moving towards understanding how ice sheets are coupled into the system by getting right what we call the cavity beneath them, which is crucial for understanding how Antarctica might change global sea level. This is where I wanted to sort of nearly finish. So these are the stupid numbers that I can't get my head around. Stupid as in too big for my sort of thinking. So floating point operations per second flops measure computer performance, and we've just been past exascale capability, which is this machine down here. The machine that I've been talking about that did the amazing simulation that was animated a minute ago had a peak performance of 28 petaflops, which was passed in, so the first petaflop achievement was in 2007. Apparently we can do over 1,000 petaflops now, which is called an exaflop. And then, yeah, it's a legacy of the Manhattan Project, I think. So I think climate modelling has a lot to gain. If we can cope with the data, that's the really big problem. And I finish almost by saying, why must we keep modelling climate? If you can bear to look at this, that's a very short movie that goes from June to July of this year. And on the right there is the amazing ocean warmth and translated into surface temperature excess, which is appearing in 2023. Bottom line is scientists are still trying to figure out why it got so warm and what lies ahead. So we know that the El Nino has something to do with this, but we don't really know. As we move towards the end of July in this animation, it gets super warm over the Grand Banks, something I've never seen. And so this is dramatic and important. Thank you. This is a picture from my recent trip to Barbados, where I also study this issue of sargassum, which is a completely different but probably climate-related problem. So I just thought I'd mention that. And I'm apparently supposed to leave you with upcoming talks. Thank you very much.
We'll go back to that. Okay.